relativity and reverse wave quantum theory are actually one and the same theory. If Einstein hadn't yet discovered relativity theory, the reverse wave theory would have predicted it.
You're talking about special or general?
Special at this point. I offer this as the best evidence I can that this theory is correct. It doesn't just explain what it's designed to explain. It also would predict special relativity, which of course has been thoroughly validated. And notice now we don't have to go through the torturous process of relativizing quantum mechanics. The reverse wave theory is already relativistic. So you've right there saved probably 50% of the work involved in current relativistic quantum theory. Now this theory extends immediately to general relativity. If you have gravity present in this example, then the gravity will affect the light because gravity affects everything, including the photons. And the curved motion of the photons is going to augment this weird effect where simultaneity is different. It's going to change the way the light makes things appear. So you're going to get general relativity, but again, it's the same thing. It's not as if space itself becomes curved. All that changes is the light that you use to observe things with. Now, I'm really running out of time, so I wanted to say quite a bit about Feynman diagrams and how they come about. What's your preference? Should I continue?
Yeah, keep going.
All right, I have all the time in the world. I don't know about all of you, but all right. I'm going through this rather quickly now. Now, at this point, I need to take a closer look at these reverse waves. I mentioned before that it's not frame invariant as I've presented it. I need the next slide. If a particle is moving, pardon me, let's say, I'm sorry. If a particle is moving to the right, following a wave moving to the left, then a transformation to a new system moving to the left would speed up the particle while simultaneously reducing the frequency of this wave, so the two would not correspond anymore. However, remember that the phase velocity, the velocity of the wave fronts, is given by c squared over v. It's an unphysical velocity. This is the standard quantum mechanical relationship. And this is greater than c, so it's not physical. And we can't fall back on the usual quantum analysis using wave packets, which do move at a physical velocity, because, again, there are no wave packets in this theory. So the dynamics of what's going on here is not that of ordinary wave propagation. Consider an analogy. Imagine a vibrating string with wavefronts moving to my right along the string. And now imagine that the whole string itself is moving to the left. Even though the wavefronts are moving to the right, I'm sorry. This has to be what a reverse wave looks like, with the string moving one way, but the wavefronts propagating the other way along the string. So the reverse wave doesn't propagate with a wave-like dynamics. Instead, it propagates as a simple flux carrying the waves with it. To make this string analogy complete, the string would have to be infinitely flexible so that the motion in neighboring points does not affect the other points. It's not an actual propagation along a string. It's just that you have all these vibrating points with the phases coordinated to make it look like a wave going in the opposite direction. Now that synchronization of all these oscillations is not an accident. It actually results from relativity. You can see this just by considering a wave corresponding to a stationary particle. The wave for a stationary particle is the same over all of space and oscillates with a frequency mc squared over h. That would be the frequency of a particle representing, a wave representing a stationary particle. Now consider how that oscillating object would look to an observer moving in the minus x direction with velocity v. I mean, you'll have to picture some of this. The particle that was at rest will now move with velocity v in the plus x direction. Because of its motion, clocks that were synchronous in the rest frame become asynchronous because simultaneity changes. This means that the phase of those oscillations will no longer be the same at different points of this vibrating object. So the uniform oscillations will start to take on the form of a traveling wave. Mathematically, at a distance L in front of the moving observer, as measured in the observer's frame, special relativity says that clocks will appear to be ahead by an amount given by this relationship. Or in the direction of motion of the particle, as seen by the moving observer, the clocks in front appear to be behind by this amount. The distance L in this relation, this is the distance in front of this moving particle. The distance L will correspond to the wavelength lambda of the wave that's produced by this change to simultaneity when delta equals this frequency, or the inverse of the frequency, when the period is equal to the inverse of the frequency. So the wavelength will correspond to one full oscillation. Let's see. So you conclude that you substitute in the expression for the frequency and the lambda for the L, and you end up with exactly the right relationship for the relationship between the momentum and the normal relativistic expression for the momentum. Now, this shouldn't be a surprise, because if you do a Lorentz transformation, of course, you get the right wave and you get the right relativistic relationship. But usually this is derived by transforming the momentum. But you can get the same result by taking the wave object and transforming it. And this shows that the phase motion is really the result of nothing more than the change to simultaneity. So it can't be a signal that's propagating. If it was, you could reverse the direction by changing the simultaneity. So the signal is carried by the flux. Now, the picture is still not completely frame invariant. You still have to worry about the velocity of the string. And the only way that can be invariant is if it moves with velocity c, so that it's c in all frames of reference. So the reverse wave object, followed by a stationary particle, is a flux with velocity c in some direction, carrying an oscillation that's the same over the whole flux. And that object then transforms into waves that look exactly like what quantum mechanics predicts under the appropriate Lorentz transformation. Now, this picture of a flux carrying the wave immediately explains another aspect of current quantum mechanics, which I always found completely incomprehensible, namely negative frequency waves. A positive energy particle will travel in the direction opposite to its flux, because it's following the reverse flux. So the flux and the wavefronts, and the particle moves with the wavefronts. As the flux goes one way, the particle goes the other way with the wavefronts. A flux with the wavefronts moving in the opposite direction of the flux itself would be what I'd call a positive frequency flux. If the wavefronts move in the same direction as the flux, it would be a negative frequency flux. So you see, you get a physical basis for understanding what it would mean to talk about a negative frequency. Simply means that you reverse the wave motion relative to the flux. Current quantum theory has no basis for making that distinction. And I'll say more about that in a moment. Now, because these waves propagate as a flux and not as a wave, they can't be viewed as waves in a medium. The flux is the medium. This flux exists independently in addition to elementary particles, which is why I call it an elementary waves, or an elementary flux.